this one integral right here truly is equal to this integral plus this integral. But since I already found that this one particular integral here diverges, then the whole thing diverges for free. I can no longer exploit that cancellation of values, particularly when it comes to bounded or unbounded, regions that do not have finite area. Yes?
You have something that converges plus diverges and gives you some funky...
Now, I don't like a choice of words. I mean, I do think both of these diverge. I didn't prove to you that this one diverges, but I've already proven this one does in my last example.
Is there an example, or is there a time when one converges and one diverges when you split it up?
You know what? I can contrive an example where that happens.
So what happens when you add one plus the other? You don't get it for free, right?
You're right. Can you hold that thought? Let me make that example up for you.
So it's also diverging, right, in different directions. One's going to positive infinity, the other's going to negative.
Now, I know. That's what I'm saying. You might want to sit there and say, gosh, it seems like the evaluation of the integral should be 0, just cancellation. But there isn't, because by definition, I have to split up two integrals. And if at least one of these diverges, then certainly some diverges.
Okay.
So infinity minus infinity isn't 0?
Yeah, thank you. Unfortunately, it just doesn't hold here, simply because one of those integrals, at least one of them, did not converge. Therefore, the sum doesn't. David, on that thought. You finish it.
Integral.
Thank you, because over that interval, what's the output? Did you guys see my point? What's the output? No, it's this. You got to choose it right after that. Plus the integral from 0 to 1 of my 1 over root x. This equals, can I play over here this time? Plus, you guys, the French technique. Yes or no? Did I successfully evaluate the second improper interval, and did I successfully show you that it converges? Yeah, I think I did. It's just that when it comes to the first improper interval, it has to be one that diverges, just like in my last example. Actually, it's just like number 6 and the other half plane. But since now I got the sum of two improper integrals, one of which converges to who cares what, one of which diverges, then I think the sum is going to diverge as well. So David, there's an example where maybe one of the terms does, one of the terms does not.
So if one of the terms does and one does not, the divergence always takes precedence?
Absolutely. Yes. I agree.
So the book also, when they say that something diverges, they like you to say which way it diverges, so infinity or negative infinity. And so in the previous example where it kind of diverges in both directions, would you just put plus or minus infinity, or do you really even care, as long as we just say that it diverges?
I actually prefer you not to say positive or negative infinity, because in my last example, I'm sorry if I'm messing up my numbers, everybody. In my original number 7, I'd hate to see you write infinity minus infinity.
We couldn't just do plus or minus and then the infinity sign?
That's fine. The reason why I don't go there is because I'm afraid somebody will confuse that with being 0.
Okay.
Which is tempting, very tempting. It would be very logical, not logical. It would be intuitive, and I think logical. It's just incorrect.
So minus infinity equals 0, remember?
Oh, sometimes it does. You've evaluated plenty of minutes last semester. It's just infinity minus infinity is anything goes. Could be anything. Could be infinity, negative infinity, or anything in between. If you're thinking of infinity minus infinity as the difference of the output of two functions, as when you take the limit as x does something. Oh, by the way, Brad,
Yeah.
I think inadvertently I've answered your question. Notice how I evaluated this improper integral, but I came up with an exact value. I did not come up with an approximation. So no decimals.
Okay. Can you go over that last step again?
Yes, I can.
Alright.
Yeah, I might have skipped over too much.
Okay.
So Brad, check this out.
Alright.
Can I write it with a sign?
Yeah.
So this equals ditto plus the limit as t goes to this thing. But you guys, if I'm going to anti-differentiate 1 over root x, or shall I say x to that power, am I not going to up the exponent by 1? Divide by the new exponent, which is 1/2, and evaluate. Now do you see?
I see. Yeah, I see how you got that. But when you took the limit as 0, as it approaches 0 from the right,
Oh, sorry. Here is my horizontal t-axis. Here's my vertical y-axis. Let me graph this equation right here. Now, as t approaches 0 from the right-hand side, certainly the y values are going to 0.
okay.
That's all I did in my head.
Plug in 0.
You know, you're right. I can plug in 0 directly because I'm not coming in from the left-hand side. True.
What if the y values were going to like 2.78 or something like that?
Well, that's
Because
fine.
I've actually found that a few times.
That means this particular term evaluates to 2.78 or whatever that number is.
Or if it just continues going on. Because I've,
Oh, you mean the decimal expansion keeps going
yeah,
on?
yeah.
Well, yikes! If there's no repetition in
Okay.
pattern, then you're dealing with an irrational number. We typically would use some other notation to represent that.
Okay.
Square root of 2, square root of
Yeah, I found a couple problems where, I solved it, and I got the right decimal approximation, but they actually had like a fraction and a radical or something like that in fully simplified terms. I just don't know how they pulled that out. I can maybe show you after class, because I
You
got
show me, 'cause
the
I just
particular
can't-
answer in my book there, or the
Yeah,
particular
show me.
question.
I'll take a peek.
All right.
You guys, is it a decent enough discussion of improper integrals? So we can kind of change the topic. Yes.
Can we get ones that like use
Oh, absolutely, yes. I can certainly give you examples where in the process of valuing those limits, you can use all the tools in your past, including L'Hopital's tool. Gosh, you guys, I don't know you from Math 30, not all of you. So we all call it L'Hopital's rule, right?
That's Bernoulli's rule.
What's that?
It's Bernoulli's rule.
Bernoulli's rule. So, everybody. I've got a population of rabbits in my garage that increase in population by 10% every month. And so if one month I've got 100 rabbits, what's going to be the change in population next month? So my population increased by 10% every month. I've got 100 rabbits in my garage on one particular month. For the next month, my population is going to increase by how much?
10%.
Well, actually 10 rabbits. You're right, 10%, but 10% of 100 is going to be 10
Yeah.
rabbits. If I had 1,000 rabbits in my garage, and the population is still increasing at a constant rate of 10%, then how many more rabbits will I have the next month?
Depending on the size of your garage.
Yeah, we won't look at that yet. 100 more rabbits. But 100 is not the same thing as 10, is it? And so I think the actual increase in my population was proportional to how many members I had of the population, whether it's 100 rabbits or 1,000 rabbits. Now, a lot of times, we assume this kind of population model, namely that the population increases at a rate that's proportional to how many members are present in the population. I've got a nifty way of writing this in terms of mathematical symbols. I have a tendency to write that the rate at which my population changes with respect to time is proportional to how many members I have in that population. It's an equation that relates the rate at which p is changing to what the p is. This is an example of what I refer to as a differential equation because it's an equation that involves the derivative of some unknown function p. And since this is a natural assumption that we often make with population models, let's see what I just run with it. Let's see if you and I can't solve this differential equation. But solving a differential equation is different than solving an algebraic equation back in Math B. To solve a differential equation means I don't come up with a number, I come up with a letter or a function for p in terms of t. Now let me show you my very first technique for solving differential equations. I'm going to separate variables. I'll write everything involving p on the left-hand side, and everything not involving p, or shall I say everything involving t, is to the other side. And now anti-differentiate, or shall I say integrate each side with respect to the respective variables integration. I have transformed the original differential equation into one that involves the integration process. This technique is called separation of variables. Now I maintain, on either side of the equal sign, life in terms of Math 30 is a 100% absolute piece of cake. And you can yell at me saying, oh, you should really have constant integration on both sides. You're right. It's just that when you bring all the constants to one side, c minus c is equal to good. I agree. And in solving for p, I guess I'll exponentiate both sides. Maybe clean up with my basic laws of exponents. Maybe isolate p completely. Maybe even rewrite my equation so it looks nicer. And proclaim to you that I have indeed solved my differential equation, and I found that unknown function for p in terms of t is just simply exponential. And if you guys think I made a mistake, let's check it. By the way, this is a Math B check. When I say check it, I mean this. Pick this up off the import. Slap it on the left-hand side, see what you get. See if it's what you get on the right-hand side. So watch me. To check to see if this satisfies my differential equation, I'll look at dp dt and see if I get well, k times p. So I check to see if I satisfy the original dE. Let's do it. So the left-hand side, I'm differentiating with respect to t my p function. But that means I'm differentiating with respect to t this function. But that's just simply, is that a times k times e to the kt? But that really is just k times p. I just shown you that I do indeed have the correct solution. Now I confess, I truly confess, that you guys, this can't be that realistic. Well, I should say, it can't be realistic in the long run because, jeepers, that's an exponential model, the solution. And you darn well that in my garage, eventually, poof, when I open the door, all these rabbits are going to be popping out. Do you think that's actually going to happen? Do you think one day I'll open my garage door and they all come flying out at me?
No.
Why not?
There's a constraint.
Well, yeah, you guys.
They'll
I don't have
probably
enough money
die
to pay for
eventually.
food. And there's that
Yeah.
many in my garage. And certainly they're going to start dying from just a disease epidemic. I think there's a constraint on that population relative to a lot of variables, but in the end a constraint. So, how about this? And I'm being very realistic. This is what we do in mathematics. We say, I think that's true. Then we analyze and say, well, I think there's a problem with it. let's just keep it but modify it. So in modifying it, I think initially populations do increase exponentially. Well, many of them do. It's just that if there's a carrying capacity of the population, there's an upper bound of what the population can be. Then as the population approaches that particular upper bound, what do you think is going to happen to the mathematical model?
Starts leveling off.
It starts leveling out. If I start leveling out, coming close to that carrying capacity, then what's the rate of change in my population?
Zero.
It's getting close to zero. And so I think if my population gets close to zero in terms of rate of change, as I get close to that carrying capacity, then maybe I can take this differential equation and modify it. Let's see. So far, it says that if p is really close to zero, there's not much change. There's hardly any members of the population. But if I multiply that by maybe L minus P, where L is my carrying capacity, this kind of makes sense. Watch. No writing. P is really darn close to L. This factor is really darn close to zero, which means this is close to zero, which means my population is hardly changing if I'm really close to my carrying capacity. Seems to make logical sense, and I think it does. Graphically speaking, here's my t-axis. Here's my y-axis. I think if y is equal to some function p and t, initially, I'll grow exponentially. But sooner or later, as I approach that carrying capacity, I'm going to have to start leveling off. Do you guys think you could say anything interesting about some point in the middle? Look at that point there. I know I can't draw very well, but it looks like that point is an inflection point, and it is. Can anybody just use their math B skills to identify where that point is? Oh, really? Using math B. If you treat dp dt as y, you treat p as x, what kind of function is y and x?
So line.
It's a.
Oh wait, no.
I'll say that all over again. If you treat this whole thing as y and p as x, what kind of equation is this?
Linear.
Quadratic. And therefore the graph is a
Parabola.
parabola. And if L is positive, K is positive, it opens
Up.
down.
Or down.
Because my leading coefficient's negative, it just isn't working, is it? And so I think if I were to graph x against y, clearly my two x, or in this case p intercepts, are at 0 and L. And is this what the parabola looks like? Yes, no? No, I can't look
Normally,
like
no.
that. Parabolas have symmetry. And I think with symmetry, my parabola's going to look something like this. But because there's symmetry, can somebody tell me at what p-value I have for which I max out at dp dt? Yeah, half the carrying capacity. But to max out with dp dt means I've got an inflection point. And I max out at the slope of the tangent lines right at that point, which occurs at what value of t? I don't know. But it certainly occurs for this value of y, namely half the carrying capacity.
But it's still half the carrying capacity when E naught is anything that's greater than 0.
Quite the contrary. I think if I start out with a population that's above half the carrying capacity, that means I'll be strictly concave down and have the asymptote. Or how about this? What if your initial population is so big it's causing a problem? Then I think I immediately start going down to the carrying capacity, and I'll be concave up to round. Oh, you know what? This is so important, I'll give it a name. I'm going to now refer to this big circle thing in blue as my logistics differential equation. It works so darn well in many instances. It even works really well when it comes to my saying something bad about Bradley. And I said it just to one person. And the rumors start spreading. The spread of rumors, or the spread of epidemics, often behaves in exactly the same fashion. I promise I won't say it.
Okay.
You guys, you know what? I've got 60 seconds. There's no way I can solve it logistics DE. So can I just slough it off till tomorrow? And we'll solve it together. Meanwhile, you guys can get some practice. Section 7.6, wait, 7.7, sorry. Do you guys think we could do something a little bit different?
Yes. Let's do it.
Because the last two exam scores are what they were. Let's try something different. You read ahead of me. Next section 7.8. So I can run with this. So part of your homework is read ahead of me, read section 7.8, so when I come to class, I'm not starting from scratch. You guys have to add some exposure to it. Fair enough? I'm sorry,